Alright, this video is going to be for chemistry, chapter 5 in Brown-LeMay, thermochemistry. Thermochemistry means, thermo means heat, so it's including heat in chemistry. I have this little sheet on your website, and basically this is just an outline, things we need to look about. We're going to talk about energy, and classic definition of energy is the ability to do work or to produce heat. It's the sum of two types of energy. From physics, you would know that there's both potential and kinetic energy. Kinetic energy is the energy of motion. Potential energy is your condition or your position. Together, it's known as the internal energy of the whole system. Okay. Now, potential energy is the energy by virtue of position. In chemistry, it might also be that we're looking at bonds. So bonds can represent potential energy, okay, forming or breaking. And one of the biggest misconceptions is a lot of people say, well, how do you get energy from foods? And when I was a student, your biology teachers would always tell you that you get the energy from the bonds. Well, then there's a misconception that energy is stored in a bond, and that's actually the exact opposite. If I'm going to break this bond, I need to put energy into the system. So putting energy into the system is endothermic. So where do you get your energy from foods? Is yes, all the bonds do get broken, but you have to make an investment in that. It's like looking at this paper right here and saying, well, I want to get energy from this paper, so I might decide to burn it. Okay? Well, you're not getting the energy from the bonds in the paper. You have to light it on fire. You have to put energy, and that energy goes into breaking the bonds. In the case of food and respiration and this paper, your energy comes from forming bonds. So when you form bonds, the energy of the system goes down. It releases energy, and that's called exothermic. In a combustion reaction, we usually see it as heat and light. Something's burning or something's on fire. Okay. In respiration, you break sugar molecules where you're literally your energy that you get from that comes from making the bonds in carbon dioxide and water. You get the same two products with paper. Paper's a carbohydrate. You react it with oxygen. You have to invest energy, but the energy that comes out of it comes from the formation of CO2 and water, and that's the same product you get with paper. Okay. Units of energy. The classical unit is called the calorie, and if you have Spanish class, you know that calor refers to heat, and it's the amount of heat needed to raise your temperature. And the classical, well, your standard for comparison is water, and water is defined as raising the temperature of 1 gram, 1 degree Celsius, and that would be defined as a calorie. When you talk about food calories, in the classical calorie, it was lowercase, was your calorie definition scientifically. In a food calorie, they would use uppercase C. That calorie today would be considered to be a kilocalorie, 1,000 small calories. So a kilocalorie is 1,000 calories, but that's your food calorie that you lose, and it has a capital C. We no longer use calorie. Our SI unit is called the joule. And today, 1 calorie, if you convert that to joules, is 4.184 joules. And that's a conversion you're going to use it often. It's a constant. It's the constant for the specific heat of water. To take 1 gram of water and raise it 1 degree, it takes 1 calorie, or 4.184 joules. Okay. I mentioned kinetic energy, the energy of motion. The equation we have for that is Ke equals 1/2 mv squared, which you probably used in physics. mass times velocity, and that's where the motion comes in. When you're measuring heat, the biggest problem with heat energy is I can't look at something and tell you exactly how much energy is in that substance. Uh, you know, the total can't really be measured. Okay, and that's because it's a little more complex than what you might be thinking. Okay, I'll kind of come back to that later when I get down to enthalpy. First law of thermodynamics, it's called the law of conservation of energy, or energy is conserved. Okay, you cannot be created nor destroyed. That's basically first law. Okay, what we do is we only transfer energy. Q, and this is one thing that confuses people. Q is considered to be an amount of heat. Okay, so almost like if you measure a chemical out and you know the number of grams of it, or if you took an amount of water, you know the amount of liters of water. Okay, when you have two different systems, the energy always flows from the warmer object to the cooler object. Okay, maybe that answers one of the big questions you've always wondered. If you open a door, are you letting the heat in, or are you letting the heat out? Or, are you letting cold air, are you letting cold in, or are you letting heat out? Generally, and this goes back to kinetic theory, things are always moving, okay? So things go from a high state of organization to a greater state of disorganization. That's the second law. Second law of thermodynamics is what we call entropy, or disorder, okay? Well, if you have thermal energy, it's always going to go from a warmer object to a cooler object. The cooler object's going to be more organized. Temperature is how you measure kinetic energy. It's proportional to the average kinetic energy of a molecule. Okay? So a thermometer measures your average kinetic energy. And then we get to the big thing, H. Okay? H is enthalpy, and enthalpy can't be measured. Okay? Enthalpy is your amount of energy at any state. Okay? Now, you might ask yourself, what's the difference between Q and H? Well, I'm going to look at enthalpy more on a graph to show you what enthalpy is. Okay, enthalpy really includes the potential energy of where it is before and after, but for all intents and purposes, Q is equal to your change in enthalpy. If you go from enthalpy at one condition to an enthalpy at another condition, well, you either released Q or you absorbed Q. If you release Q, then Q is considered to be negative. You've lost it. So your change in H will be negative. If you absorb Q, if you absorb heat, then that's considered to be a positive quantity, so your delta H. Now, we can't measure the amount of heat in a system, okay? But we can measure the change in the heat. So when we see delta H, that's what we can measure. Now, delta H, for all intents and purposes, I just told you it equals Q. There's one big difference. When you get a delta H, you divide it by the number of moles of your substance. So whenever you see units for delta H, the units are going to end up being kilojoules per mole. Okay, Q is usually just joules. So for me to go from a Q to a delta H, I have to convert joules to kilojoules. That would be dividing it by 1,000. And then I have to divide it by the number of moles of substance. Okay, so H is always usually done on a per mole basis. You see in here that it's got kJs per mole. Okay, Q is just the amount. So I'll try and make that. Now, there's all kinds of enthalpies you can have. The enthalpy of a reaction. You can have the enthalpy of a combustion reaction. You can have the enthalpy of formation, that's forming any chemical from its elements. What's the enthalpy for that? You could have fusion. That's the heat it takes to melt a substance. Okay, So when you melt a substance, you got to put heat into it to overcome those attractive forces. That would be a heat of fusion. Heat of vaporization would be going to a gas. Now it takes a lot more heat to go to a gas than it does to a melt. Melting, all you got to do is overcome those intermolecular forces. Vaporization, you got to get them very far apart because it turns into a gas. So I'll give you a little bit of modeling. There you go. Let's get them all stacked together. Now, if this was a system and we were at the coldest possible temperature we're at, so let's get it out to so we're like no energy at all, and that would be at absolute zero. At absolute zero, all motion stops. If I looked at this system is more simplistic. Everything would just be atoms. Okay, so if I had a bunch of atoms. So if I started taking this from 0 degrees, what you would start getting is vibrational energy. It just starts vibrating. And I think you guys have learned that usually with solids, when you add heat to them, they expand. And the expansion's due to those vibrations. Okay. There's 3 types of well, this came from a guy, Austrian guy named Ludwig Boltzmann, and pretty severe looking guy. But what Boltzmann did is he looked at systems and called them microstates. And so when he looked at it, he said, well, what kind of motion can I have? And the first type of motion you can have is if they just move straight. Okay. And if they were moving in like a straight line, when we draw skizzies in a box, get them all to move around. Okay. That would be called translational motion. Well, we also saw a second motion, which was just vibrating in place. That would be vibrational. And if our atoms could rotate, that would be a third rotation state called microstate, called rotational energy. So when you get to the different types of energies, you see it gets more and more complex. 2 objects next to each other feel an attraction. Okay, that's an intermolecular force because everything's made of atoms. All atoms are made of protons and electrons. So the protons from this one can attract the electrons of this one, or the electrons of this one can attract the protons of this one. These are called, we call them IMFs, intermolecular forces, if it's a molecule. And every atom has intermolecular forces, and this is what we pretend they don't have when we say it's an ideal gas. Well, real gases do have IMFs, okay? So that creates a whole different type of force. The fact that these two have a force of attraction between them. And in the case of just getting to move like this, that would be our heat of fusion, the heat that you have to overcome to have them sticking together. If I convert them to a gas, so if I got them away from each other and broke that intermolecular force, well, that's more energy that I have to add. So that's our heat of vaporization. So that's where you can see the heat of vaporization come in and the heat of fusion come in. Okay, and that sometimes when you hear something as a state function, that means it depends what state it's in, because the energy can change with states. Okay, and I'm going to bring this in. If I had a molecule, then I get a whole different world. Okay, if I get a molecule, my rotations look like this. I can get vibrations and I can get translational motion across. But then within the bonds, you can get many other types of energies. Okay, the first one is you can get bonds bend. So you can have waggles, and that's another microstate. And this is why you can't figure out how much energy something has. It's a very complex system. I could have compressions and rarefactions, so the bond can spring like this. So you can actually get bond vibrational energy and waggles. So once you get molecules involved, now it becomes way more complicated. But we'll try and simplify it. Okay. When we talk about energy, we can talk about the systems and the surroundings. And usually our classic look is just like a box. Here's my box. So the energy of this box would be the energy of the system. and outside the box would be the surroundings. Okay, together the surroundings and the systems make up the total universe. Well, the law of conservation of energy says that it's always conserved. Okay, between both. Okay. I have no idea how I have this camera rigged up, but it's scary. All right. Energy can come out of this box and be released, and that would be energy released would be exothermic. So directionally, I could say the energy is coming out of the box. Okay, exothermic. Exothermic because the energy inside this box will be going down, and that would be considered to be a negative delta H. The energy going out would be a Q. Okay, so if the energy came in, if I had a Q come in, like I pump the energy into the system, something you can actually do in your house. It's called a heat pump. You do it in a refrigerator all the time. Okay, this is like inside your refrigerator. Okay, inside the refrigerator, you're normally pumping the heat outside the refrigerator, which is why your kitchen is normally the warmest room in the winter, because it's constantly exothermic. The heat's coming out of the box. Okay, pumping heat in. Okay, say you're inside an automobile, you can pump heat inside the automobile, so the surroundings and the system would be inside your car, and it would get warmer, things would move more as you pump heat in, and that would be considered to be endothermic, heat going into a system. And together, the system and the surroundings make up the universe. So we can pump heat in, we can pump heat out, but as a net in the universe, the change in energy is zero. Okay, so the one on the left, we're pumping heat out. Your change is negative. So exothermic, the change in enthalpy is always negative, saying that you lost heat. What messes kids up is if you had that in your hand, it feels hot. So when something feels hot in your hand, the heat you feel is the heat that's coming out of the system, but the system is actually decreasing in energy. But you don't see that you don't see any temperature change expressing that. Okay, to you it feels hot, but to the substance inside it, it's going down in energy. Okay, so it's going negative. When you're gaining heat, your change in H is positive. So gaining heat is endothermic. So an endothermic system absorbs heat. Okay, an exothermic system releases heat. Delta H is negative, delta H is positive. That heat coming in and out is what we would call Q. Q out, Q in. Okay. Normally when I see Q, I don't really put signs on it. Delta H, you always want to have a sign on it. But I always just tell people to make it simple. Just think whether the heat's coming or going. Okay. Heating curves. Potential energy diagrams. Okay. They're right here, but if I'm going to draw a potential energy diagram, okay. Say I have a reaction where I'm going to take water. Well, I'm going to take hydrogen plus oxygen, react it to make H2O. So let's add 2 hydrogens and make 2 molecules of H2O. This reaction would be exothermic. You see me do this when I blew up the Pepsi bottle in front of the class. That's a release of heat. Okay, so if I start in the beginning, this would be potential energy. This is what we're going to call enthalpy, H. Okay, and these would be my reactants. So I have 2H2 plus O2. Okay, at the end of the reaction, and this will be progress. So at the end of the reaction, these are lower, H2O. And then from where you started, here at this level, down to here, well, that's my H at my first position, H1. This is my H at the second position. Well, that's my delta H, okay, which is equal to negative. And this would be exothermic. So in the reaction, I can say plus heat. Heat would be a product, okay, although it's not a, although heat's not a form of matter, we can write what's called the thermochemical equation, where we include heat in our equation. Okay, now in between this, it just can't go straight down, because what you have to do is you have to break the bonds in hydrogen and oxygen. So you have to add energy to this, and then it comes back out. The energy that you have to add, we call the activation energy, just like the energy to get it started. Activation energy is the energy required to break bonds. Okay. So what do we know? We know our delta H and we know our EACT from the top to the bottom. Okay. And this energy is released. That's why it's negative. Okay. If I did the exact opposite reaction, if I took water and I put electricity through my water electrolysis to break it as a decomposition reaction, okay, now instead of heat coming out, I have to, I said heat, but I really should say energy. So I have to invest energy in that. You have to run electricity through that reaction to make it go backwards. Well, if I flip this reaction backwards, now my products are low. So these would be my products here. Now all I've done is flip the reaction, and these become my reactants. So my reactant would just be water. My product now exists at a higher energy state, 2 hydrogens plus an oxygen. H is your potential energy. This is the reaction progress. Just means as it proceeds, start slow. You got to go up higher again to break the bonds in water, and then it comes back down. Okay. From this base here all the way to the top, it's called my EACT. And then the difference between where I was and where I end up, that's my delta H, my change in enthalpy, and now it's positive, so it's absorbed. And that makes this a endothermic potential energy